Okay, last time we started into discussing Faraday's major discovery. Early on in his researches of electricity and magnetism, he had the idea that since you could, in effect, make a magnet from electricity, if you take an electrical coil and take a coil wire and send a current through it, that coil becomes a magnet, right? So from electricity, you could get a magnet. Faraday's idea was, well, there must be some way of turning this thing around, and from magnetism, actually generating electricity. And he started into trying to do that in the 1820s, and the first attempts were unsuccessul. He tried various arrangements of magnets next to wires and hooked the wires up to galvanometers to measure to see if he got any current, and he never got any current. Now, he finally figured out how to get a current. And if you remember, the first experiment, experiment, I guess we just called this experiment 1 last time. The first experiment that he tried that actually worked, he had an actual, a donut, a ring of iron, and a coil around one side hooked up to a battery, and then a coil around the other side that was hooked up to a galvanometer to measure any current. And what, you remember what happened? Somebody tell me what happened. When he hooks up the battery here, what does he see, Daniel?
The galvanometer, the needle that tells
yeah.
its power quickly moved from 0 to 1, and then after a while it came back to 0.
Right, there was a momentary deflection of the needle showing a current over here. But it was only momentary, and then it would go away. And then when he unhooks the battery here, there's also a little deflection of the needle that he sees. So that gives Faraday the idea that, he now begins to understand why his previous experiments hadn't worked. He always had a steady magnetic field, okay? This time, what's happening, he's only seeing the current generated here when the magnetic field is starting up through this coil or when it's going away. Okay, so because what's happening here is there's no connection between these coils, remember. The only effect that this coil hooked up to the battery is having on the coil on the opposite side of the ring that's hooked up to the galvanometer is by causing this ring to be magnetized, right? When the current flows through the coil hooked up to the battery, it magnetizes this iron, which then suddenly creates a magnetic field through this coil hooked up to the galvanometer. Okay, it's when that magnetic field is created through this iron and through this coil that you get a current. As soon as the magnetic field is just steady through the coil, current goes away. Okay, so it's when the iron becomes magnetized, at that moment it creates the current. When it becomes demagnetized, when you turn off the current, then you get another current, a surge of current. Okay, but it's only when there's this changing magnetic field through the coil that you generate a current. So Faraday decides to check this out more directly. Okay, so let's say this is now experiment number 2. Let's say we just have a galvanometer here. So there's my needle. And then we have a coil of wire hooked up to it. And now we take a bar magnet and we move it into the coil. Then.
That block is, what's that block?
Oh, this?
Yeah.
Oh, this is just the galvanometer. So there's a, if the needle deflects, then we know we've got a current. Okay? So a current through this wire will cause this needle to move. So what's going to happen when we push this bar magnet into this coil? Okay, if Faraday's right on the basis of his first experiment, it should cause a current, right? And sure enough, that's exactly what he sees. He sees the needle deflect. Now, let's say he pushes the bar magnet into the coil and then just holds it there. What's going to happen?
It's going to reflect and slowly go back to normal.
Yeah, I mean, not even very slowly. It'll, as soon as he stops moving this bar magnet, basically, the current's going to disappear. So he's, on the basis of that first experiment, that gave him the idea that the magnetic field has to be changing in order to create an electric current. And sure enough, it's easy to show that with this kind of setup, that if you're moving the magnet, you get a current. You stop moving the magnet, the current goes away. Nick?
Was like the little jolt of electricity, that current that it was getting, was it stronger than they could produce, or was it just the normal amount?
Oh, well, I'm going to talk about ways that you can use this effect to create a really strong current. So this can cause a lot of current. So it's not a small effect. Now, so this is, I mean, This is a huge discovery, right? People only knew of one way to create electric current at this stage. That's with batteries. Okay, there's no battery here. There's just a coiled up wire and a bar magnet. And all you have to do is move the bar magnet into the coil and you get an electrical current. Now, true, it goes away if the magnet stops moving, but and
Was it up to this time nobody had discovered this earlier just by accident? Because it seems like that would happen by accident faster than.
oh, you know, I think that this is one of those effects where you have to be looking for it. Because let's say that you had a coil of wire or a loop of wire, and you happen to have a pretty strong magnet in your lab, and you move the magnet with respect to the coil, and let's say you even noticed a momentary deflection of the needle. You had your loop hooked up to a galvanometer, and you even noticed a little, you know, the needle tweaked a little bit to one side and then went back to zero. What would you think? You'd think, well, geez, something must have jostled that galvanometer, or maybe my galvanometer's on the fritz or something. The needle made a weird little movement, but it's back to zero now, so it's normal. So you wouldn't think anything of it. I mean, there's a lot of cases like this in the history of science where people, you know that the major discoverer of the effect was not the first person to see this effect. He was the first person to realize how important the effect was, you know, that he was looking at a brand new phenomenon. I mean, there's all kinds of cases like this in the history of science. If you think back on the discoveries of Galileo and Newton, Galileo was not the first person to see that a pendulum swings back and forth in the same time, no matter how big the swing is. Okay? People had seen things swing back and forth for thousands of years before Galileo. He was the first person to pay close attention to it and realize that this was a law of nature, and then relate it to free fall and all these other things. So it's Faraday had the knowledge that enabled him to actually think there might be an important new effect here, and then set up an experiment to specifically look for it. And that's why he was the one that attributed significance to this needle deflection. Okay. Now, all right, now what about the direction of this current? Now it turns out there is a way to figure out what the direction of this current has to be. I'm tempted to ask you, but it's a little tricky. Now the way I've drawn it here, I'm pushing the north pole of this bar magnet into the coil. Now do you think that's going to cause a clockwise or counterclockwise direction to the current in this coil? Well, let's think about it. Let's just guess. Okay, let's say that it's counterclockwise. Okay, now if the current goes counterclockwise through the coil, well, that current will create its own magnetic field, right? And what direction would that magnetic field be in? Let's say we had a counterclockwise current. So the current is going around in this direction. Okay, that would actually create a magnetic field pointing in this direction. Okay, so let's write that down. So if we're symbolizing current by I is counterclockwise, then magnetic field is to the right, as I've drawn it on the board. And in other words, it's in the same direction as the magnetic field of the bar magnet. So let me put it that way, is in same direction as field of bar magnet. What?
Looking from which direction,
The oh.
Which side of the coil are we
Oh, right. From the, I'm saying counterclockwise, looking from the direction that you're pushing the bar magnet in. Okay, so, okay, now I know, hang on. I'm not, if, this is hypothesis, this is just a guess. Okay, I'm not saying the current's going in that direction. I'm just saying that imagine that, I mean, there's two possible directions, right? If you look at it from the, Ben?
would be the other way?
If the current,
Your current's going this way.
He's saying this.
oh, I'm sorry. I'm sorry. If you look at it from this way, it's clockwise, right? Right. Okay, so, yeah. Look at the, I had my hands going in the right direction, and I was just saying counterclockwise instead of clockwise. So if we look at the coil from the direction that we're pushing the bar magnet in, now the current that is created by that bar magnet going into the coil can be in one of two directions, right? It can be clockwise or counterclockwise. So, okay, let's say my first guess is clockwise. So the current's going around this way. Okay, that will actually create a magnetic field in the same direction as the magnetic field of the bar magnet. Okay, so we would have this situation. If we push a bar magnet into this coil, okay, that changing magnetic field through the coil creates a current, okay? And we're assuming, okay, it creates a current going clockwise in this case, which creates an additional magnetic field through the coil, right? Okay, the current itself will create its own magnetic field. Now, that means that the magnetic field through the coil is changing some more as that current is generated, right? Which will in turn generate more current. I mean, if a changing magnetic field generates current, then the current will generate its own magnetic field, right? That'll create more current. that more current will create more magnetic field, which will create more current. So you would have the current just increasing indefinitely until the wire just melted and evaporated on you. Now that doesn't happen. So obviously I guessed wrong about the direction of the induced current here. You see how that would lead to just a runaway situation where there's where you would get indefinitely large currents, and that that doesn't happen. So, in fact, the current is generated counterclockwise. Okay, it always and the way to current is always generated in the direction such that its magnetic field opposes the changing external field. I don't know whether that's the clearest way to formulate that, but you get the idea that if you're increasing the magnetic field through this loop of wire by pushing the north pole of a magnet into the loop, the current that creates in the loop will always be in the direction to create a magnetic field that opposes that change in the magnetic field from the bar magnet. Okay? Is that clear? So loops of wire are they're conservative in this sense. They oppose change. They'll always fight you when you try to change the magnetic field through them by creating a current which opposes the change in that magnetic field. Okay? But this is a radical new way to generate electricity. And it's the way that, that led to the whole electrical age, because in fact all of our power plants, they don't consist of enormous batteries. Okay? They consist of enormous coils of wire and huge magnetic fields. And basically the whole power plant is set up to do one thing, to cause a motion of these magnets with respect to these coils to generate huge amounts of electricity. I mean, that's all Hoover Dam is. I don't know, have any of you ever gone to Nevada and seen Hoover Dam?
Seen it, I didn't spend time there.
Oh, okay. I mean, it's a great place to walk through. I mean, the dam itself is incredibly impressive. It's, I mean, this huge wall of concrete holding back this whole enormous river, the Colorado River. And and then they let the water through, okay, I mean, down below where there's inlets to let the water through. Well, the water comes rushing through. It's under enormous pressure. It spins these huge turbines, okay? I mean, this is what the job of the water and the whole dam is just to let this fast-flowing water through under tremendous pressure and turn these enormous turbines that are connected to huge iron magnets and coils. Copper coils as thick as your wrist, okay? I mean, wound many, 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 many times. And all they're doing is creating relative motion between super strong magnets and these coils, setting these coils spinning in super strong magnetic fields in order to create a huge changing magnetic field through a coil of wire. That's the whole purpose of Hoover Dam. And then it generates, as a result, this enormous amount of electricity. So this discovery of Faraday opened the way for the whole electrical age. Okay, now, let's see, I wanted to tell you about a couple of other interesting experiments that one can do to demonstrate these sort of effects. This new effect that Faraday has discovered. And here's, let me call this the flying ring experiment. It just gives a dramatic illustration of exactly the point that I just made about the direction of this induced current. If, let's say we have a cylinder, say of iron, that we've wrapped a coil around. And we attach it to let me see, I probably should have, oh well. We attach it to a current source here. Let's see. Now, we put a ring, say an aluminum ring, on the top of this thing. Now, when we turn the current on here, turns out that this ring will come flying off. Now, why would that be? Well, yeah, Selah.
Well, maybe they're just like two forces that sort of repel.
Yeah, now where have we seen currents repelling before? If you think back to Ampere, if you have two parallel wires, right? If the currents are in opposite directions through those wires, what happens? They actually they attract. No, they attract if they're in the same direction, right? Let me see. If you have them in opposite directions, okay, this wire that I've drawn on the on my left will create a magnetic field into the board here, right? And then the force is you point your fingers in the direction of the current, curl them in your thumb, curl them into the magnetic field, and your thumb goes in the direction of the force on the wire, right? So it's going to, if the currents are in opposite directions, they repel. If the currents are in the same direction, they attract. Okay, so in this case, if I put the current through my, say, my coil of wire that's wrapped around this iron cylinder, if I put that, say, going clockwise, well, as soon as that current starts up, it's going to create a changing magnetic field through this aluminum loop that I've laid on top, right? Okay, that's going to cause a current in that aluminum loop, right? But what direction is that current going to be? It's going to be the opposite direction of the current through the coil, right? In order to, because it wants to oppose that change in the magnetic field through the loop. So it's always going to cause a current in the opposite direction. Because we just went through that with, if it created a current in the same direction, then we would have that unstable situation where the current would keep getting bigger and bigger until the thing melted down. So the induced current, the generated current in this aluminum loop, the aluminum ring, due to the changing magnetic field, is going to be in the opposite direction. Well, oppositely directed currents repel each other. So this ring is just going to kick off. So that makes for a dramatic way to illustrate exactly the effect that Faraday had already seen about the induced current always being in the direction to oppose the change in the magnetic field. Okay, now remember when Ampere, well, in the early 1820s, when Ampere and Faraday were first experimenting with the forces on electric currents generated by magnets. They figured out how to make an electric motor, right? We talked about that the last time. And the motor that I remember that I told you about, simple motor where you put a say a rectangular wire in a magnetic field. This is the side view, and we worked out that let me see. In this case, as I've drawn it, we would have a force going in up top. We would have the current through this wire forcing the loop to my left, and at the bottom we would be having it kicking it to the right, and so there would be you can get a loop of wire to spin in a magnetic field like this. You just put current through it, and you see that it creates motion. Well, with Faraday's discovery now, let's go back to this same case, and let's say that rather than just putting current through the wire and then seeing it move as a result, okay, that's a motor because you're transforming electricity into external motion. Well, let's say we don't put a current through the wire. Okay, we have this same setup, only we just have our rectangular loop of wire in there, and we connect it to a crank. And we just start spinning this loop around. Okay, what's going to happen? Neat.
Then they get a current with electricity.
Right, right. And why? Can you think of what's causing that current? Yeah.
Because each time it moves 180 degrees, the force will reverse directions, so it'll continue changing.
Right. I mean, there's always going to be, as long as you're rotating this loop of wire in here, there's always the amount of electric field going through that loop is always changing, right? I mean, think of it this way. Let's start out with, so let's say your loop is in this horizontal plane. Okay, so the magnetic field now is vertical, so it's directed right through the loop. Okay, you're getting a maximum amount of electric field directed through your loop. But when it turns 90 degrees now, and so it's oriented vertical along the magnetic field direction, well, is there any magnetic field going through this loop? No, right? Because the direction through the loop would be horizontal, and there's no magnetic field in that direction. So you've gone from, having a maximum amount of magnetic field going through your loop to having 0 a quarter turn later to, after it turns another 90 degrees, having a maximum amount of field through the loop but in the opposite direction. Okay, so as you turn your loop here, the magnetic field through that loop is constantly changing. And so you're going to generate a current through that loop. Now, what's the direction of that current going to be? Will it always be in the same direction? You're shaking your head, Ben.
Well, you said that it keeps changing, so.
Yeah, I mean, sometimes the magnetic field through your loop is increasing, and at other times in the turn it's decreasing, right? So the generated current in that loop is always going to be opposing the change, but the change is in different directions at different times during the rotation. So it's going to create a current that changes directions constantly. Now, that's called, does anybody, as opposed to DC, which is abbreviated direct current, a changing current like this would be, oh, that's a good guess, but Nick, AC, alternating current. Okay, that's what AC stands for. That's what we have coming out of the wall sockets, is alternating current. In fact, it alternates the current coming out of the wall sockets it alternates 60 cycles per second. Okay, so, 60 cycles per second. So, that's 60 times a second. Okay, it's changing directions. And that's what lights up all of our lights. So current, the current from batteries, just a straight battery is always in the same direction. That's DC current. But with a simple electrical generator of the kind I just described, you generate AC current. Yeah. Oh, okay. Now, so notice that there's no real difference between an electrical motor and an electrical generator. In fact, you can, I'll explain at the, we're out of time this morning, but this afternoon I'll explain how you can have the exact same setup can be a generator or a motor, and in fact you can have a generator run a motor run a generator. Depending on, you crank one, you generate the electricity. Okay, so you're taking external motion, your muscle energy, and turning it into electricity in the case of a generator, and in the motor you're just doing the opposite. Okay, to be continued.